Hello everyone, I'm Jianlei Yang from Beihang University. I'm glad to present our paper entitled Towards System Education for Artificial Intelligence, a course practice in intelligent computing architectures. In education community, there have been many courses focusing on AI applications and algorithms, but always lacking a computer system or architecture focusing on AI topics. Since 2017, there are several courses focused on AI chips, including UIUC, MIT, and Stanford University. From 2018, several courses are focused on AI computing systems, such as Professor Yun Jichen from University of Chinese Academic of Science, UC Berkeley, and the University of Washington, Georgia Tech. Our course started from 2017 in Beihang University. Our course is mainly focused on intelligent computing architectures. We will newly start a new course in 2020 focused on intelligent computing systems. Our course mostly aims to bring the research frontiers into course teaching for training students' computer system capabilities in AI era. By taking this course, students could have a full-stack AI techniques training. But this course requires very broad knowledge and skills and very strong practicality. Our course requires several prerequisites. Firstly, students have to take the courses including computer organization, operation system, compiler principles, as well as the computer architectures. And also some circuit and system developing courses are required, including digital circuit and system, the Verilog hardware design language, and the FPGA design. And also some basic introduction of machine learning methods and C or Python programming skills. After finishing our course, students could further take the course or system for machine learning. The main task of our course is to design AI chips. From the technical perspective, students should first know some machine learning algorithms and applications. And also they are required to learn some AI-specified computing architectures aiming to improve the energy efficiency. An important problem to finish this task is how to map machine learning algorithms and data flow to the hardware efficiently. The answer is the software-hardware co-design techniques. The main contents of our course are listed as those 7 parts. The core parts are how to design hardware architectures and how to map the algorithm to such hardware designs. Our course labs are designed with 4 steps. The first lab is to program a neural network with the C language or Python language, aiming to understand the basics of neural networks. The second lab is to evaluate some deep neural networks with some popular frameworks, such as Caffe, TensorFlow, and PyTorch. The third lab is to design some basic circuits in Zinc FPGA to let students get familiar with design methods, design tools, design environments, and some many other techniques. And the final lab is to design a matrix multiply and accumulate module with Verilog and evaluated and validated in our FPGA design platform. For course projects, we have 3 designs. The first project is to design a Mac module in Zinc FPGA. With this project, students could understand how to design heterogeneous system. The second project is to design an ARINITE on zinc FPGA. For such a network, only on-chip block RAM is enough, while no off-chip DRAM is required. But for the final project, they are required to implement an VGG net on zinc FPGA. For such a large-scale network, off-chip DRAM have to be utilized to store their huge number of model parameters, and also students could do some performance evaluation and efficiency analysis. In our course, a simple architecture design is provided as a reference, as shown in this figure. Similar to Google's GPU, a reduced version with smaller MAC array and a smaller memory utilized is adopted in the reference design. Besides the computation units and the memory hierarchies, another important thing is to formulate the proper finite state machine and generate the instructions streaming. Since 2017, our course has been iterated for 3 years. For each year, we have about 30 to 50 students for taking our course. For about 80% of students could finish our Lab 1, Lab 2, Lab 3, Lab 4, and Project 1. And about 60% of students could finish the second project. The second project aims to design the ARINITE on zinc FPGA and demonstrate their functionalities. For the final project, to design the VGG NITE on zinc FPGA, which is very challenging and very difficult. Only about 15% of students could finish this task and demonstrate their design correctly. We also have collected many students' feedback. From the analysis of those feedbacks, we have many conclusions and further considerations. For myself, I have spent many time to prepare the courseware and lab materials. And for students, they also spend much more time in our course than taking other courses. Some students feel that this course is too difficult to finish, but some students have very strong interest to finish those challenging tasks. Most of those students said they could learn a lot in our course. But we also have a little bit consideration, that is our course too difficult for undergraduate students? I'd like to show a project example in 2017 here to demonstrate whether undergraduate students could really accomplish such a complicated project. The project is named FPDL. Here is the top-level data path as shown in this picture: the on-chip memory, the input-output buffer, the processing unit array, and the controllers, as well as the input and output data path. Taking a CNN as an example, the network model is abstracted as weights and instructions. And for data flow mapping, the weights, states, and instructions are loaded separately into the FPDL architectures and stored in different memory space. For running the data flow, the input states are loaded into the I/O buffer, as shown here. And for COM kernels, those weights data are loaded into the C memory space here. For the fully connected layers, the weight data are loaded into the wide memory space here. And the activation functions are performed in the ALU processing logics here. And most important, their computation data flow are controlled by the instruction streaming, which is loaded into the instruction memory space here. They use different memory space to store different data or instructions. Their design is evaluated on a Xilinx Kintex 7 FPGA board. It could run at about 100 MHz. Compared with the Tegra K1 GPU, they could obtain about 20 times speed up and reduce about 50% power consumption. For power efficiency, it could improve the efficiency about 40 times than K1 GPU. Here is the LPDL's demonstration for handwritten characters recognition. As shown in this video, it could work very well. Okay, that's all. Thanks for your listening. You are welcome to give some questions or discussions.